In second part of our topic of NMR and IR, we will discuss about the shielding and deshielding of the photons. So let's take the example of this compound. In this, there are the two trans proton. One neighbor is the methyl and another neighbor is the carbonyl group. Unexpected carbonyl proton should be more deshielded, but in this the carbonyl protons has less delta value as compared to the methyl neighbor proton. Methyl neighbor has 6.8 delta value and carbonyl neighbor has 6.2 delta value. This is due to the resonance effect of the pi bond. So whenever the protons are nearer to the pi bond, that proton has less delta value. In second compound also, the proton nearer to the carbonyl has less delta value 5.9 rather than the other proton that have more delta value 6.8. In this second example, the proton which is nearer to the methoxy group has more delta value because it is directly attached to the oxygen atom. Oxygen is more electronegative. And another one which is nearer to the methyl group has less delta value. It is more shielded. That's why delta value is less 4.6, and which is nearer to the oxygen has more delta value 6.2 due to more deshielding effect. In the ring, the proton which is nearer to the oxygen has more delta value due to deshielding effect of oxygen. So another effect, that is the effect of steric hindrance on the chemical shift. If there is a steric hindrance in the ring or in the given compound, then that increases the delta value. In this first ring, the proton nearer to the OH group has less delta value 3.45, but in second compound the axial proton has more delta value, that is 3.65. This is due to the steric hindrance produced by the methyl group in the second ring. Similarly, in methyl benzene and isopropyl benzene, the proton nearer to the isopropyl group has more delta value as compared to the proton nearer to the methyl group in methyl benzene. This is due to the steric hindrance produced by the isopropyl group. So what is anisotropy? So anisotropic effect is the shielding effect due to induced magnetic field produced by the pi orbital electrons in the same molecule. If whenever the induced magnetic field protects the proton from the applied magnetic field, then such protons are called as the anisotropic protons, and such a proton absorb at the low delta value in the NMR spectroscopy. So let's take first example of the ethylene protons. In alkene, the protons are attached to the double bond orient perpendicular to the applied field. These protons are attacked by the applied field. At the same time, these are also attacked by the induced magnetic field which is produced by the pi electrons in the same compound. If we observe, at the site of the proton, the applied field attacks on the proton. At the same time, induced magnetic field also attacks on the proton. That's why such protons are deshielded and they absorb at the higher delta value than expected, that is more than 3.5 delta value. This is second example of anisotropy in benzene. So what is about anisotropy in benzene, or what is about the delta value in benzene protons? The benzene, we know the benzene proton absorb in between 7 to 8 delta value. These are highly deshielded. So why it is so? In this, if we observe, the induced magnetic field of the circulating pi electron attacks at the site of protons, means these protons are not protected from the applied field by the induced magnetic field, but these protons are attacked by both the fields, because when benzene is oriented in the when benzene is taken into the applied field, then it orients perpendicular to the applied field. Then these protons are attacked by both induced field and applied field. That's why their delta value is more higher than alkene protons also. The third example of this type is the anisotropic effect in case of the acetylene protons. If we observe the alkyne anisotropy, means in acetylene, if we observe the protons are attacked by the applied field, but at the same time these are protected from the induced magnetic field due to the circulating pi electrons, because the circulating magnetic field due to pi electrons is in the opposite direction of the applied field at the site of protons. So the protons are protected by the induced magnetic field from applied field at both sides, above and below sides. This below side protected and this is the upper side protection. That's why these protons are shielded protons and they absorb at the lower delta value as compared to the ethylene protons. So in this we will observe the electronegativity effect and anisotropic effect in the same compound. If we take the examples of the methyl cyanide, and we can also take another example of the methyl chloride. So the methyl protons of acetonitrile appears at the 1.97 ppm, while that in methyl chloride appear at the 3.05 ppm. So why it is so? If we think about the electronegativity, chlorine is less electronegative than cyanide. So cyanide proton should have more delta value as compared to the methyl chloride proton, but it is not so. This is due to the anisotropic effect. In case of the methyl cyanide, the anisotropic effect is present. That's why they observe at lower delta value, even though the cyanide group is more electronegative. So in this, the simplification of spectra is given here. In NMR spectroscopy, if we get the complex splitting or complex pattern of the peak, then we can simplify that peaks by using a higher frequency of the NMR instrument. In this, the three NMR instruments are given. First NMR instrument has 60 MHz frequency. Second one has 100 MHz and third one has 300 MHz. If we observe the peak difference delta V is same for all the instruments, that is 0.3 ppm. But if we multiply it by instrumental frequency, then that factor increases. In first one it is 18 Hz, in second one 30 Hz, and in third one it becomes 90 Hz. So due to increase in delta V value, we can have more delta V by J value, and that's why we get more simplified peak. This can be shown in figure 1. The peaks are complicated. In second one, the peaks are separated, and in third, that is the when instrument is 300 MHz, the peak has more separation, and so the peaks are clear. So this is the actual peak in different megahertz instrument. If instrument has 10 MHz frequency, the peak of we observe single peak, that is the complicated peak. It is difficult to analyze such a peak. But as the frequency of instrument increases from 10 MHz, 60 MHz, 200 MHz and 300 MHz, then we can see that the peak separation becomes more and more clear. In 300 MHz instrument, we get the clear peak. These peaks are given for ethyl group. Both the peaks of CH2 group and CH3 groups are quite overlap to each other in 10 MHz instrument, but in 300 MHz instrument we can clearly observe the peak which is located to the left hand side, that is given portrait, and this is due to the CH2 group, and the peak located at the right hand side giving reflect, it is due to the methyl group. So this is the example of one compound. That compound is having molecular formula C8H14O2. In this, the different peaks are given here. The peak, let us read it from RHS to LHS. The first peak, that is to obtain at near about 1 delta. This is due to the TMS effect. The second, which is obtained at 2.06 delta, it is also complex peak, and these two peaks at 2.06 delta and 2.05 delta are due to the CH2 groups. The peak which is obtained at more than 4 delta value, this is due to the deshielding effect, and these peaks are the due to the deshielded protons which are nearer to the carbonyl. Thank you.